Okay, I'm not sure where that last video left off, but I wrote down the formula for sine of A minus B. Then you take your pictures and you plug in numbers. So sine of A would be opposite over hypotenuse, negative 2/3 from the picture. Cosine of B is adjacent over hypotenuse, so negative 6 over radical 61. And we're going to move the radical 61 to the top. Cosine of A would be adjacent over hypotenuse from your A picture. Sine of B will be opposite over hypotenuse and move that radical 61 to the top. Then you want to multiply, so on top negative 2 and negative 6 are going to make positive 12. 3 times 61 is 183. On top here, radical times a radical, so you're going to have 305 inside, and on the bottom you're going to have 183. And they have a matching denominator. So you're going to have 12 radical 61 minus 5 radical 305 all over 183. B is done the same way. I'm not going to take time to do it. You can go ahead and try it if you want. Use the cosine property on the other side of your notes and use this exact same picture to fill in the values. Example 3, they want us to use composite properties to find sine of 15. So we're going to use our 30, 45s, and 60s and all those other special angles to make 15. One easy pair would be 45 minus 30. So that would be A minus B. If you look at your composite properties, that's sine of A, cosine B, minus cosine A, sine B. Actually, the one we just used in example 2. So now you're going to plug in 45s for all your A's and 30s for all your B's. And again, that's because they subtract to make 15, which is what we want. And then evaluate them. Sine of 45 we know is rad 2 over 2. Cosine 30 we know is rad 3 over 2. Cosine 45, rad 2 over 2. And sine of 30 we know is 1/2. Multiply your radicals, you get radical 6. Multiply your denominators, you get 4. Multiply the numerators, you get radical 2. Multiply your denominators, you get 4. And they have matching denominators, so go ahead and put them into one big fraction. Example 4 tells you to use cofunction properties. So we're going to rewrite this as a complement. So cosine 75 could be rewritten as 90 minus 15, because 90 minus 15 is 75. Well, when it's written this way, if you look at your cofunction table, you'll see that this equals sine of 15. And then sine 15, we just evaluated. We just found sine of 15 using composite properties. So now we already know the answer to this. And that is all you would do for example 4. In example 5, you're going to condense this down to something simpler because we're trying to solve for theta. And we can use our composite properties to do that, because this looks like an AB plus an AB. And so if you look at how the sines and cosines are mixed in the order that they're in, you'll see that this is sine of A plus B. The A in this case is theta, and the B is 35. So we can condense it down to just sine of theta plus 35. Now we're going to solve for theta. So we're going to do inverse sine of both sides. And this is to isolate our theta. That is the whole goal. Now we're going to evaluate that. So we know sine is 1/2 at 30 degrees. It's also going to be 1/2 at 150 degrees. So we can write 30 degrees plus 360n. And we can write 150 degrees plus 360n. And if you want to go ahead and use your purple table from chapter 1, you can find where sine is positive 1/2, and you're going to see 30 and 150. We still need to subtract 35 from both sides because we're trying to get theta by itself. And so we end up getting one general solution will be -5 plus 360n. And then over here, we're going to get theta equals 115 plus 360n. So those are our two general solutions. And general solution, that's why we have this plus 360n, because we're just going to keep going full rotation, full circle to get the next angle in quadrant 1 and quadrant 2. But this is actually now quadrant 4 and quadrant 2, but don't worry about it. So here we've got general solutions. Now we're going to take those solutions and we're going to find all the answers between 0 and 360. So -5 is not between 0 and 360. So if you add 360 to it, which is what this is telling us to do, you get 355 is one answer. And then on this one, 115 is already between 0 and 360. So 115 is the answer from that solution. An example, well, this next part, it's in radians. So if you look at the mixture of sines and cosines, and the fact that we've got a's and b's, you're going to see that this is cosine of a minus b, and my a is 2x, and my b is x. So that'll all condense using your composite property, cosine a minus b. Now these x's are compatible, so you can actually subtract them. And then we're just going to solve for x. So you're going to do inverse cosine to the other side. You're then going to evaluate when is cosine -1, and that only happens at pi. And so then you're going to add 2 pi n to make it a general solution. Now from there, we want to find all of our solutions between 0 and 2 pi, because that is what it says in the directions. And we see that pi is between 0 and 2 pi. And if I add or subtract 2 pi, it wouldn't be. So that's my only solution, is pi. In this last example, we're going to start on the left and we're going to prove the right. So I'm going to expand this using sine of a plus b properties, composite. And then over here, cosine a plus b. And we're going to expand that using its composite. So sine of a plus b would be sine of a cosine b plus cosine a sine b. That is the first parentheses. Then over here, cosine a plus b is cosine a cosine b minus sine a sine b. So now it's fully expanded into two different parts. Now we've got a lot going on, but anything with a number, you can actually plug in what it equals. So evaluate those. So I've got sine of theta, cosine of 30 is radical 3 over 2. Then we've got sine of 30 is 1/2. Then we've got cosine 60, which is 1/2. And then we have sine of 60, which is radical 3 over 2. And then collect like terms. We've got positive sine radical 3 over 2, negative sine radical 3 over 2. So those cancel each other out, they make 0. You've got 1/2 cosine plus another half cosine, which makes 1 full cosine. And then we're done. That's what we wanted to prove.